Starting from this lecture, we study stability, which is one of the three main topics that we aim to cover in our course. We study stability from two different points of view, which are close related to one another. First, we study so-called internal stability of a system, okay, which has to do with the following question: do solutions of an autonomous system x that equals f of x, let's say. Of course, we'll be studying it mainly for the linear system, but this subject, stability, is a very general topic for dynamical systems. Therefore, it's equally valid for the general case x that equals f of x. So, do solutions of some autonomous system starting close to an equilibrium point stay close to that equilibrium. Okay, so that's roughly the question behind studying this subject, internal stability. Okay, so in other words, under this title, internal stability, we'll be studying the response of a system due to its own initial conditions only. Okay, so we will not let external inputs interfere with the dynamics in our analysis. An example would be, for instance, the pendulum. Okay. So suppose that this is our system. It's pivoted here at this point, and it can rotate on this plane, okay, freely. And suppose that this is the angle of displacement from the equilibrium point, where this indicates the direction of gravity. Okay. Now this system, as we all know, has two equilibria. Okay. One of them is that the pendulum is pointing down, and the other is that the pendulum is pointing up. So equilibrium and the character of that equilibrium. Okay, so one of the equilibriums is theta dot. This is the state of the system, angle and angular velocity, 0, 0. Okay, so according to our notation, this corresponds to pendulum standing still, pointing down. So this is the lower equilibrium point, and the other is theta dot equals pi 0. That's the pendulum pointing up, okay, upward equilibrium. So we know from everyday experience that the equilibrium that's pointing down has the property that if you, okay, suppose that your system is at that equilibrium pointing down, if you slightly disturb that system, okay, by making theta and theta dot something small, and you observe the solutions of the system, you will see that the solution will stay close to the equilibrium point. Okay, even if there is no friction, slight disturbance will make the thing oscillate. Okay, and the magnitude of oscillations will never grow, so it will always be bounded oscillations. And if there is a friction, which normally there would be, it's also is converging to the equilibrium point. Okay, so more as time goes on, the oscillations will lose power and the pendulum will settle to the equilibrium point. So such character is indicated by the word stable. Okay. On the other hand, if you consider the equilibrium, that somehow equilibrium that's pointing up. Okay, so the pendulum is pointing up, and it's suppose that it's standing still. There are no disturbances. If you slightly disturb the equilibrium, okay, from that the pendulum from that equilibrium point, what's going to happen is, no matter how slight your disturbance, it will start gaining speed, and after a while quickly depart from or move away from the equilibrium position. Okay, and because of that behavior around this equilibrium, which is that the pendulum is pointing up, such character of the equilibrium point is indicated by the word or adjective unstable. Okay, so we have a single system with two equilibria. One of those equilibrium points is stable, the other is unstable. Okay, so therefore it doesn't make sense from the grammatical point of view to say that the pendulum system is stable or the pendulum system is unstable, because stability is not a property of the system, okay, formally speaking, but it's a property of the equilibrium of the system. Okay, but of course this adjective stable or unstable very frequently used, and we will also use it for our linear systems to indicate a system. Okay, so we say this system is stable or this system is unstable. When we do that, we inherently assume that our listener knows what equilibrium point we're talking about. Okay, so, and for linear systems, the equilibrium that we'll be interested in is always the origin. Okay, so when we say such and such linear system is stable or unstable or exponentially stable, we actually mean that the origin of our system is exponentially stable, or the origin of our system is unstable, and so on. Okay, so let's put that important note down. Stability is a property of an equilibrium point, not necessarily the system. Okay, so this is one of the subjects that we will study under title stability. Okay, the other way that we will look at the problem of stability is from the input-output point of view, and when we study that type of stability, namely the input-output stability, we will try to analyze the response of a system to the external inputs. Okay, so that's the other type that we will study, input-output stability. Okay, and this problem, the second problem, roughly has to do with the following question: do well-behaved inputs produce well-behaved outputs, or do small inputs result in small outputs? Okay, for instance, that may be an important question for some analog filter. Okay, suppose that this is our input, some sinusoidal signal, okay, epsilon with some magnitude cosine omega t, and what we do is we collect the output as the voltage of the capacitor somewhere in the circuit, and then for certain applications, it may be important the relation between the output and this input. And when that relation is important, we will be studying it under the title bounded input, bound output stability. Okay, so for such systems, it's important whether small input magnitudes produce small magnitudes at the output side. Okay. Okay, so we begin with the first one, namely the internal stability. It's also called Lyapunov stability, and then we're gonna move on to input-output stability, which we'll study under the title bounded input, bound output stability for a linear system. And we will also make the necessary connections, important connections between two types of stability. Okay. So let's therefore concentrate on now internal stability. It's also called Lyapunov stability. Okay. So what we're going to do now is we're going to first introduce the definition. Okay. So that system is, or an equilibrium point is, stable, unstable, or asymptotically stable, and so on. And then we will try to figure out certain conditions on the system parameters so that those behaviors are realized or not realized. Okay, suppose that this is our linear system, which may be time varying. Okay, so we put the general notation on the board. U and y equals ctx plus dtu. Okay, this is our system, system 1. X being the state, y the output, and u indicating the input. Okay, rk. And then these are matrices, possibly with time varying entries, and the dimension of those matrices are clear from the sizes of the corresponding vectors. Okay. Now, we're now ready to define certain types of internal stability. Okay, so system 1, our linear system, is said to be, okay, now in this definition we treat stability as if it's a property of the system. So what we really mean is that we're talking about the behavior of the solutions around the equilibrium point. That's the origin for our linear system. System 1 is said to be 1, stable, okay, if the solutions stay bounded for all initial conditions. Okay, stable in the sense of Lyapunov, okay, or sometimes called internally stable. If for each initial time indicated by t0 and initial condition x t0 equals x sub 0, the homogeneous state response Okay, x of t equals the state transition matrix t0 times the initial condition is bounded. Okay, so we don't care about what the input does, so we just exclude the effect of input if there is such an input on the system, and we only look at the homogeneous part of the solution. And if it's bounded, then and if it's always bounded, then system 1 is said to be stable in the sense of Lyapunov. In other words, okay, given any initial condition Rn and any initial time t0, if we can find some constant, okay, C, a positive constant, such that when you start the system at t equals t0 from this initial condition x0, for all future times, for all t larger than t0, the norm of the solution, okay, x of t, is smaller than some constant c, such that norm of the solution less than that constant for all t greater than or equal to t0. And by solution we mean this homogeneous solution, okay, disregarding the effect of the inputs if we have any inputs. So that's very intuitive definition of stability. Now, there are other behaviors that we also want to label, namely asymptotic stability and exponential stability. Two, the system is said to be asymptotically stable, which is a stronger definition than definition of stability, if on top of stability it also satisfies that as time goes on the norm becomes, or the norm converges to 0. Okay, so the solution gets closer and closer to, in the limit, to the equilibrium point at the origin. So asymptotically stable in the sense of Lyapunov if it is stable and for every initial condition x t0 equals x0, we have the following convergence: x of t converging to the origin as time goes on. Okay, and even stronger definition is exponential stability, where this convergence is of exponential nature. Okay, the system is said to be exponentially stable if we can find constants okay, k and lambda, one to quantify the overshoot, the other to quantify the decay rate, such that norm of the solution can always be upper bounded by that k times e to the minus lambda t minus t0 times the initial norm of the state of the solution. And this inequality is satisfied for all times, for all future times, t greater than or equal to t0. Okay. So note that as we go from 1 to 3, the definition becomes stronger and stronger. In other words, if your system is exponentially stable, then it's automatically asymptotically stable. If your system is asymptotically stable, then it's automatically stable. Okay. And finally, whenever your system is not stable, therefore it cannot be either asymptotically stable nor exponentially stable either. Okay. So such system is called an unstable system. Okay. So a system is said to be unstable in the sense of Lyapunov if not stable. Okay. That means if there exists an initial condition and initial time such that if you run the system from that initial condition and initial time, you can never be able to find some constant such that the norm is bounded for all future times. No matter what, no matter how large you pick C, after some time, t0, it will get outside that bound. Okay, such system or such behavior is called unstable. Okay, now one thing to notice is that first our definitions, these definitions has nothing to do with the output, therefore it doesn't have to do with the matrix C and D. Furthermore, it's defined through the state transition matrix, and state transition matrix depends only on the A matrix, okay, not on B matrix or C or D matrices. Therefore, this system is stable or asymptotically stable or exponentially stable and so on if and only if this system here, x that equals at times x, is stable or asymptotically stable or exponentially stable. Okay, so for simplicity therefore and without loss of generality, we will be studying the stability for this homogeneous case, x that equals ax. So let's put that down. Remark. This definition has nothing to do with matrices B, C, or D. Okay? Hence, when studying Lyapunov stability, we can simply consider the differential equation x that equals ax. Okay, x that equals a tx instead of the more general description of the system. Okay, system 1 instead of the system 1. Okay, so since stability can be, or the Lyapunov stability can be studied for this differential equation, it means that whether a system is stable or not, or asymptotically stable or not, and so on, has to do with this A matrix only. Okay, and what we will do, we will figure out properties of the A matrix that implies or is implied by these particular definitions. But before that, let's try to visualize these definitions, stability, asymptotic stability, and exponential stability, okay, over some simple diagrams. Okay, so suppose that our system is second order, so that we can draw the phase portrait on the board. The horizontal axis, let's say, representing x1, and the vertical axis representing x2, for instance, the pendulum system, theta and theta dot. Okay, so the system is said to be stable if we set all the solutions remain bounded. So that means no matter where you start from, x0, let's say, so this is where you start from, and then you also pick a time, t0, initial time, if your system is time varying, to start your system from, and then once x0 and t0 are fixed, the question is, can we find a constant, some c, such that, or in terms of this picture, can we find a circle, large enough so that when we start the system from this point x0 at time t equals t0, does the solution for all future times remain inside that circle? Now that circle can be arbitrarily large, but once it's fixed, we cannot play with it, so it has to hold for all future times. For instance, we pick this x0 and then we pick some t0, and what happens is that as time goes on, x of t moves on the phase portrait, but it never leaves this circle that we have found, and if that's the case for any initial condition, then we say that the origin or the system is stable, it's a stable system where x of t is phi t t0 times x0, phi being the state transition matrix. Now, if a stable system also satisfies the additional property that it's not leaving this ball, this circle, for all future times, but on top of that, it also converges toward the origin, let's say. If you have such a behavior, and if that holds for all initial conditions and all initial times, then your system is not only stable but also asymptotically stable. So this is asymptotic stability. A very simple picture. And furthermore, if when you quantify that decrease, that convergence toward origin, if you can do that using an exponential envelope, that is t minus t0, this is 0. So this is where you start from, x t0. So this is the initial norm of your solution, and then from this there will be starting from this point there will be a solution, and then what you do is you compute the norm of that solution for all times t minus, for all times t larger than t0, and then this norm, this function of norm, norm of x of t, so this is x of t, x of t. If you can find two numbers k and lambda such that starting from k x t0 norm, if this decay, if this decaying envelope, which can be characterized by k x t0 e to the minus lambda t minus t0, So if this norm of x of t always remains below this envelope, then this decrease is called exponential decrease, and the system is said to be exponentially stable. Okay, so this is exponential stability. Okay, now this definition is made for a linear system, possibly time varying. Now we will apply this definition to the LTI system. Okay, x that equals ax, and from our earlier analysis, namely the behavior of the state transition matrix e to the at, we will be able to instantly obtain conditions in terms of the eigenvalues of the A matrix that guarantees these properties. Okay, so therefore this is our first theorem based on previous analysis on stability. Theorem. An LTI system x that equals ax. Okay, we may also have some B, C, and D matrices in our system description, but internal stability or stability in the sense of Lyapunov depends only on the A matrix. So for simplicity, we just write x that equals ax. And now we're considering an LTI system. Okay, so A is a constant matrix. So this system, LTI system, is said to be stable. Okay, if what? Now, we studied this problem, that is the behavior of e to the at, as time goes on. Okay, as time goes on, at length, okay, in our previous lectures. And we had, what we did was, using the Jordan form of A, we showed that this behavior is closely linked to the eigenvalue locations of the A matrix. And now what we're interested in the behavior of x of t, or the property of, or the definition is given in terms of the behavior of x of t, and we know that x of t equals, for the LTI system, e to the at times x 0. Okay. Now, since this is constant, the behavior of x of t should inherit should inherit the behavior of e to the at. Okay, and we know that the behavior of e to the at from the point of view of eigenvalues of A. Therefore, we can take those conclusions that we have obtained earlier for e to the at and apply to this definition, stability definition, that we have just introduced. And if you do that, this is what you obtain. The system, the LTI system, is stable if, okay, no eigenvalue belongs to the open right half plane. That is, all the eigenvalues are with non-positive real parts for all I. And if you have an eigenvalue on the imaginary axis, that is, if for some eigenvalue lambda I, if the real part equals 0, then the size of the corresponding Jordan block, Ji, must be 1 by 1. Okay, so this must be 1 by 1 block. Okay, and by lambda I we mean the eigenvalues of the A matrix. Note that the condition is if and only if, so therefore it's both necessary and sufficient. In other words, stability can be completely characterized for an LTI system through the eigenvalues of the A matrix. So that's very nice. Furthermore, the system is asymptotically stable. First of all, well, asymptotic stability has to do with this decrease. And whenever there is a decrease for a linear system, for a solution of linear system, that, because of the solution of this LTI differential equation, that has to be an exponential decrease. There is no decrease through such terms, 1 over t. Okay, so things like that happen for nonlinear systems only. And whenever you have a decrease, whenever we have a convergence for a linear LTI, for an LTI system, it must always be exponential. Okay, therefore, asymptotic stability and exponential stability are equivalent for an LTI system, which may not be equivalent for an LTV system, and they're definitely not equivalent for a general nonlinear system. So asymptotic stable and exponential stability are the same thing for an LTI system. And we have asymptotic stability, that is, all the solutions always converge to the origin if and only if, we remember from our studies on e to the at, if and only if all the eigenvalues are on the open left half plane. Okay, in other words, if and only if real part of all eigenvalues are strictly negative, okay, for all I. Okay, once again, this is the eigenvalue of the A matrix. And it's unstable. Okay, here, unstable if it's not stable. And in order for a system to be stable, both of these conditions should be satisfied. Therefore, for instability, what we have to do is we have to negate that statement. That is, either this or that must be violated. And when it's violated, either one of those conditions, then we have instability, okay, directly. So this last thing that we write is simply a negation of the first statement. An LTI system is unstable if either there exists an index such that we have an eigenvalue with positive real part, or we have an eigenvalue, okay, on the imaginary axis whose Jordan block is size 2 by 2 or larger, or there exists an index such that the eigenvalue is on the imaginary axis and size of the corresponding Jordan block is 2 by 2 or 3 by 3 or 4 by 4. Okay, so anything larger than 1 by 1. Okay. So thanks to our analysis on e to the at earlier, we have this theorem, and all the statements in that theorem are necessary, or all the conditions are necessary and sufficient. Okay, we have if with a double F and another if with a double F. Okay, here are some simple numerical examples, okay, of x that equals ax, where we have different behavior depending on the a. Let me put it on a table. So we have here the stable column and unstable column. Stable and let this column be unstable. And here we have an asymptotically stable column that's automatically also stable. So here are some systems. X that equals minus 1, 1, 0, 0, x. X that equals 0, 1, minus 1, 0, x. Or x that equals 0, 0, 0, 0, x. Here we have x that equals 0, 1, minus 1, minus 1, x. And here we have some unstable examples. 0, 1, 0, 0. And here we have x that equals 0, 1, minus 1, 1, x. Okay, so let's go system by system and apply that theorem to determine the stability properties of each of these 6 systems. Okay, so let's begin with this guy here. What we have is, first, the eigenvalues are clear because this is in diagonal form, this triangular form. So it has the upper triangular structure. Therefore, the entries at the diagonal are the eigenvalues of this system. So we have an eigenvalue at minus 1 and eigenvalue at 0. So both eigenvalues satisfy this condition. Okay. And so this is a second order system and we have 2 distinct eigenvalues. Therefore, the Jordan form for this A matrix must be simply diagonal matrix with entry minus 1 and 0. Therefore, all the Jordan blocks must necessarily be of size 1 by 1. So this is an eigenvalue with negative real part because it's at minus 1, and here we have an eigenvalue on the imaginary axis. Since the size of the Jordan block corresponding to it is 1 by 1, we say that this system is stable. How about asymptotic stability? Although this system is stable, it's not asymptotically stable because for asymptotic stability we require that all the eigenvalues must have negative real parts, but here we have an eigenvalue on the imaginary axis. Therefore, that condition is not satisfied. Hence, the system is stable, but not asymptotically stable. Okay, now for this system, this is skew-symmetric matrix. All the eigenvalues on the imaginary axis, and in this case, it's easier to see that, or you can compute it easily. The eigenvalues are at plus minus j. Okay. Again, all the eigenvalues. We have no eigenvalue with positive real part, so all the eigenvalues satisfy that property. And since we have 2 distinct eigenvalues, the order of the system is 2, therefore all the Jordan blocks must be of size 1 by 1. So both for eigenvalue at j and minus j, the size of the Jordan block is 1 by 1. Okay, therefore this system is stable. And since the eigenvalues does not satisfy that, because both are on the imaginary axis, this system is stable but not asymptotically stable. Now here is a very boring system, x that equals 0. Okay, so that means any point on the plane is an equilibrium point. You start the system there, it remains there. Let's check the eigenvalues. This is already in diagonal form. Okay, the eigenvalues are both at 0. And since it's in diagonal form, it's already in Jordan form, so we see that all the Jordan blocks are size 1 by 1. So even though all the eigenvalues satisfy that, the sizes are also 1 by 1, therefore the system is stable. It's clearly not asymptotically stable because this condition is not satisfied. Okay. Now, as for this system, the characteristic polynomial for the A matrix is s squared plus s plus 1. So we see that the eigenvalues are with negative real parts. In fact, it's a complex conjugate pair with real part at minus 1/2. Since this condition is satisfied, it's automatically asymptotically stable. We don't have to check anything else. We don't have to check any Jordan blocks or something like that. How about this last column, unstable matrices? So here we have a matrix. Here we have an A matrix that's also like here in upper triangular form. Therefore, the eigenvalues are both at 0. Now, this A matrix is already in Jordan form, and it's clear that the Jordan form, the Jordan block that corresponds to the eigenvalue at 0 is size 2 by 2. In fact, the A matrix itself is the very Jordan block that we're talking about. Okay, since even though the eigenvalues satisfy that, the size of the Jordan block is 2 by 2. Okay, that is, it's larger than 1 by 1. Therefore, this system is unstable. Okay, as for this system, if you compute the eigenvalues, you're going to see that you have one at least one at the positive, with the positive real part on the open right half plane. Therefore, this condition is satisfied at least for one eigenvalue. Therefore, automatically this system is unstable too. Okay.